Cool. So we saw what the first version of the reader-writer problem is, right? So if a process is writing onto the shared memory space, nobody else gets to do anything with that memory. But if no writer is working on the memory space and a reader comes asking for access, immediately it should be given access, irrespective of whether there is another reader already or the memory space is not being accessed. That is the core idea. And you also have to ensure that while readers keep getting preference, a writer which came in between should not have to wait indefinitely. So starvation should also not be there. That's the idea. And we have to come up with a solution for this using semaphores. That's what is going to be the focus of this segment. So we're going to use three variables and we look at the solution. Semaphore RW mutex equals 1, semaphore mutex equals 1, int read count equals 0. So semaphore RW, okay, both of these semaphores first of all are binary, meaning they can both take either 0 or 1. We initialize them to 1. Semaphore RW mutex. So if you remember the producer consumer problem, we had this buffer which is analogous to our shared memory space here, the shared object or the common location where some processes are reading and some are writing from, right? So that's like the buffer. So in your producer consumer problem, you had this lock kind of mutex kind of a variable. Whichever process acquires it, only that process is allowed to use the buffer, right? So if the producer has it, producer can write, but consumer cannot read at that time. The consumer has it, consumer can read, but producer cannot write at that time. Same logic extends here and we call it the RW mutex, just naming convention. Again, you're free to use your own choice of name. So RW mutex, if a reader process has acquired RW mutex and set it to 1, it means any number of readers can access the memory location at the same time. But no writer is allowed to go in at that time. Whereas if a writer process has acquired RW mutex and set it equal to 1, only that particular writer is allowed to access the memory. No other reader, no other writer also is allowed to touch that memory location. Which makes sense because we saw writing is very critical in the sense that when one process is writing, nobody else, be them reader or writer, should be allowed to touch. So yeah, RW mutex basically is the lock you put over your memory space. If a reader acquires it, all readers can read. If a writer acquires it, only that writer can write. And whoever acquires it, once they are done with it, they will release it. Again, there's a catch in that also. If the writer has acquired it, the writer will write. Once it is done, it will release. If another writer wants to write, it will separately acquire and then it will separately write, separately release, so on and so forth. With readers on the other hand, reader R1 may acquire it. When I say reader, writer, I mean reader process, writer process. It's understood. So R1 might acquire it, R2, R3, R4 might join in, and then R1 will finish reading and walk out. R2, R3, R4 will still continue, then R2, R3 will finish and walk out. R4 will finish and finally R4 will release the mutex. So it is important to understand that in case of readers, the process which acquired the lock need not necessarily be the one which is releasing the lock. So one will acquire, multiple will use it, and then whoever is the last to finish reading, that process will release the lock, and that is perfectly fine. So that about RW mutex. Now I'll come to semaphore mutex. We'll see int read count is the number of readers who are accessing the memory location concurrently at any given time. So readers, you can have multiple readers, right? So this is the number of readers. Initially nobody is doing any reading or writing, so the value is equal to 0. Now semaphore mutex equals to 1. This lock, this again is a binary semaphore, a lock which is used to update the value of this variable read count. Why do we need that? Because see, multiple readers are going to be reading at the same time. So if R1 and R2 are coming in, both of them will want to increment this read count by 1, right? So every time a reader comes in, read count has to be incremented by 1 unit. So if R1 and R2 both try to increment at the same time, it means two processes are trying to write the value of a variable at the same time. And two writings at the same time is chaos, right? We've seen that enough times already. So even if two processes are reading the memory at the same time, they should not be allowed to update the read count at the same time. For this updation, they need to take turns. So to make sure of that, we have this variable called mutex, which is a lock over this read count variable. We'll now look at the code and hopefully things will be clearer. We start with the writer process. Very simple, very straightforward. Writer has nothing to do with read count, so it won't even go there. While true, it will acquire the RW mutex, which I told you, if you remember, is the mutex for the shared memory space. So it will acquire the lock for that memory space so that nobody else can interrupt. It will write whatever it wants to write, and then it will release that mutex. Simple enough, straightforward. Now we move to our reader process. So here a little more work is happening here. So in the reader process, what happens is it first acquires the lock for mutex. Mutex, let me remind you, is the lock for updating this variable. So the reader process comes, it wants to read, it does not even go to the memory location first. It first wants to register that I am going to be reading. So it wants the lock for this variable. So if someone else is currently updating, it will have to wait. Or if a writer process is writing, then it will not be allowed to do all of this. So once it gets access to read count, it will increment read count by 1. So whatever number of people were reading initially, now I have joined them, so read count is incremented by 1. Then if read count equals to 1, meaning if this process, this reader who came in is the first person to be coming in. So if initially read count was 0, this person is the first one to have entered, which means no one else was previously reading, right? In that case, it will wait for RW mutex. Now why? See, if someone had already been reading, okay, if read count was already a 2 or a 3 before this process came, it means the memory is already under the control of the readers. This RW mutex is already in the hands of the readers. So this reader can simply go and join the other readers in reading, correct? But if nobody else had been previously reading, so this guy who came in is the first one to ask for read permission, then there are two possibilities. Either your memory is currently not being accessed by anyone, it is totally free and available, or some writer person is already sitting there and writing. In either case, you being the first reader to make the request, you have to acquire the lock for yourself and for the readers to come after you. So if this process is the first reader, it will ask for permission on the lock pertaining to the common memory. Then now I have updated read count, so I don't need this lock anymore. I will release this lock, mutex corresponding to the read count variable. I still have the reader lock. Now I'll do my reading. I've finished reading. Now I'm going out. So I have to decrement read count, right? So I was one of the people reading. Now I'm done reading. I'm leaving. I have to decrement the number of people reading. So again I will get the mutex. I will mutex corresponding to this variable. I will decrement this. Now I'll check if read count equals 0. If nobody else is reading, then I will release the lock on the shared memory also. So this again I said, right, R1 might take the lock, but when R1 has finished reading, R2, R3, R4 are still reading. So R1 will just walk out. It won't give up the lock. R2, R3 will finish, they will walk out. Then when R4 is done, nobody else wants to read. It is R4's responsibility to release the lock on the memory location. So for that, the reader will check, am I the last person to be reading here right now? Is there no one else who wants to read this location? If so, once it is done reading, it will give up control. Then it also releases control of this read count variable. So what is happening here is, for a writer it is very simple. It will just wait until whoever is currently working on this memory location, whoever it may be, writer, reader, whatever, it will wait until they have finished, it will write, it will give up control. As simple as that. For a reader, there is a little more work. It will first wait to deal with the read count variable. It will wait for access to that. Once it gets access, it will increment. Then it will check, am I the first reader around here? If yes, it will ask for access for the memory location. If not, access is already with some fellow reader who is reading, so it will just go join. Now it has incremented read count. It doesn't need this variable anymore, so it will give up that lock. Then it will sit and read. After reading, again it wants to decrement read count. It will wait for access. It will decrement it. Then it will again check, am I the last person reading around here? Is no one else left? If so, it is finished reading, so it will give up control of the shared memory, and then it will also give up the other mutex. So that is how we use semaphores to solve the reader-writer problem. So what were our requirements? If a writer is writing, nobody should be given access. Is that being fulfilled? Yes, if a writer has the lock, nobody else is being given access. Whether it's another writer or reader, nobody is getting access. The writer took the lock, only after he finishes writing, he gives back the lock. Cool. Next requirement, if nobody currently is using the memory location and a reader comes, it should be given access. So at this point, if read count equals 1, this fellow is the first reader. Assuming there was no writer also, then when you give this wait RW mutex, it obviously gets access immediately, right? Again, I will urge you, if you're not sure about the definitions of wait and signal functions, to revisit the segment about semaphores where I've explained these. So the wait function is defined such that if nobody is currently using this common resource, give immediate access to whoever is coming first and asking. So if this is the first reader to come and no writer is currently using, this function call will immediately give access to this person. That is there. What else? Multiple readers should be allowed to read at the same time. Yes, they are being allowed. We saw that R1 might take access, and then R2, R3, R4 will join, and finally R4 can give up access once it is done. That is totally working under this code. And when one writer is writing, no one should be allowed to read. So whatever conditions we had, all of that is being satisfied, right?